Hello, and welcome to It's Dangerous to Go Alone. Listen to this, an engineering and gaming podcast. I'm Aubriana Hansen,
And I'm Gavin Hagen.
and we are definitely qualified to do an episode on earthquake detection technology. We are both very much qualified. Um, we're definitely not self-taught. This is a very this could be used as a source in your academic paper.
Yes. This right here is a part of the abstract.
hmm It's just a link to this podcast. Anyways, welcome to the obligatory hard science episode, Earthquake Edition.
Yay.
Today, I forgot to take my notes out, so I will be taking my notes out quickly.
So do we need some like fun questions, some fun trivia here?
We should we should actually implement that in future episodes. And by the way, this is staying in. All of our off-topic conversation, including fourth wall breaking stuff, even if it can even be called fourth wall breaking, is staying in.
I mean, hey, trivia's fun. I mean, I'm trying to think of things off the top of my head, and the first thing that comes to mind is like the singular term for a parenthesis. Well,
Isn't it a parenthesis?
yeah, it's a parenthesis,
I mean, it
but
makes sense, but like it's a weird word.
it is. I'm trying to think of more fun trivia, but that's the first thing that comes to mind.
I got my notes up now, and allow me to preface this episode with this is probably going to be a very niche episode. I'm not 100% sure who this appeals to, but I do know that there will be up to 20 people, of roughly 20 people, who will be forced to listen to this. So here are some a quick rundown of the big topics we're going to be talking about. LiDAR, which is satellites and it's mapping out Earth's surface. That's used in earthquake detection. INSAR is somewhat similar. We'll be doing a deeper dive on that one. Creep meters and alignment arrays are both more physical ways of. I say physical. Satellites are a physical thing, but they're on the ground and they detect earthquakes and we can see our magnitude from them. So you were able to probably get down a fact from that. Uh, Feel free to check out for the rest of this episode.
Just goes into a conspiracy theory. What do you mean? Satellites aren't real?
Obviously, well, you believe space is real?
Well, you think the Earth is not the shape of a velociraptor?
I can't believe that we are hosting an anti-science podcast. We're not Velociraptor Earth deniers. You're not welcome on this podcast.
I'm sorry.
Just saying.
I'm sorry. If you came on or you started listening to it and you thought that the Earth was not the shape of a velociraptor, you know where to find the door. I mean,
Oh,
not a door,
and
but you know what I mean.
to clarify for our regular viewers, no, we do not have a hostage situation of 20-something people who we have kidnapped and we pre-screened the episode with them. This is part of a class that this is being used for. Do not be concerned. We are not kidnappers.
Yes. I also have to. This is true. This is factual.
Alright, so let's get into the meat of this episode. With our first topic,
Or
creep
tofu or
meters.
something if you're vegan, I guess.
Oh
And you
yes,
got yeah,
vegans, you welcome to the tofu of this episode. Yes?
maybe the tofu. Or maybe like rice or
Welcome to the plant-based substitute of this episode.
oh, my next one was gonna be quinoa, but you could go on a little ways, or beans or okay, I'm done.
Yeah. So this is the model, a basic model of what a creep meter is. Basically, you measure how much the invar rods move and how much the pebbles move between the iron bars, and that tells you how much the Earth has shifted since it was last recorded. You generally record about every 10 minutes with one of these. And welcome to how we
Um,
are relating this podcast, this podcast episode to to current events, if you will.
um,
Now, in this trailer, as you can see, Bowser shakes the earth with his magma. If there was a creep meter around here or around here, it would pick up something from that. It could, but it could possibly just think that it was basic weather anomalies because you could see how much the ground was shaking there from just reloaded to about a second. You can see with how much the ground was shaking there, a strong wind could also create that much ground shaking. Now, that, that, if it did not destroy the creep meter, would definitely set it off.
Are you sure it wouldn't melt it?
Like I said, if it did not destroy the creep meter.
I will say that is probably the derpiest version of Bowser's face ever.
Yes. Regardless, now that we got our first topic down, it's very simple compared to the other ones. We can move on to alignment arrays. You need to utilize your basic trigonometry knowledge for this one. I gotta reset this slide. I forgot to reset this slide. Um, this is definitely our first take of this episode. This is
Yes,
100% our first take of this episode. We never do multiple takes. This is definitely the first take of this episode. Forget that I have to reset this slide. You saw nothing.
if a man named Craig ever says anything otherwise, he's wrong and a liar. I will not elaborate on this reference.
They absolutely will not get this reference.
We're not going to elaborate on it either way, so it's fine. They don't need to worry about
Um,
it.
so yeah, here's the basic setup of your alignment array. Go back. Go to back. Okay. Here's your basic setup. We are a very professional podcast. This is a very professional presentation.
Yes. Yes, we do this, definitely do it for a living. Definitely.
So this is how your alignment array basically works. Your instrument is um I apparently did not write this down. It is it should be in my search history. It's a theodolite. It's one of these bad boys. Not one of these. And maybe in the past it would have been one of these. Though I'm not sure how long we've been using alignment arrays specifically to measure creep. That should also be mentioned. That's primarily what creep meters do as well. They basically measure how much a fault has shifted, so you can predict whether or not an actual earthquake will happen. Alignment arrays are very similar as well. These record every 10 minutes. These record every. Well, you have to manually record it, so it doesn't automatically record, but surveys are generally done every 6 months to a year. And it also should be said that the instrument is the only actual piece of technology, so to say. It's the only theodolite. Basically, they have to have waypoints. So the orientation target and the end target do not have any advanced technology on them. They're basically a pillar with a reflective surface so that the theodolite can use infrared rays. Well, specifically in modern ones, infrared rays. I admittedly only looked up modern earthquake prediction technology. I did not look into historical earthquake prediction technology. But at least with modern ones, you have to bounce off the orientation target and the end target in order to get a proper angle, which you can sort of see here, which I need to bring this to front now. Yeah, so as you can see here, the amount of creep is measured by getting the angle from ES1 to OS and ES2 to OS, and getting the difference. Pretty basic trigonometry here in order to get that. Obviously, if OS is no longer perpendicular for whatever reason, IS and OS are supposed to be on the same side, so there would be some major issues if it shifted too much to not be in a vaguely perpendicular angle. It doesn't have to be perfectly 90 degrees, but then you have to have the data from past surveys in order to get it because it would no longer be a perfect right degree angle. We're back to hard math now.
The fun math.
Um, yeah, I just went on a rant about trigonometry and didn't really let you get a word in edgewise. My apologies, Gavin.
I think I missed part of that.
I sort of just went on a rant about trigonometry and did not let you get a word in edgewise, so apologies about that, Gavin.
Oh, that was fine. I was just kind of I didn't want to interrupt.
It also has come to my attention with you not getting all of that last line that I may have been talking too fast for that entire explanation.
Oh no, you're
But
fine.
that's a problem for editing me.
Yeah, that's a problem for yeah, that's a
And
problem
I
for
do not
future
have to
you.
worry about that right now.
The or I was thinking about I mean I know we passed it, but the creep meter or not the creep meters, the
Alignment array?
or sorry, yeah, the alignment array
Hmm.
or oh no, I'm mixing up terms. Oh no.
This is the creep
Yes.
meter, this is
Okay.
the alignment array.
I was thinking creep meter. That I was just thinking because once again, this is definitely our first take, and this is definitely the first time I've asked this question. Don't mean to break the fourth wall, but the so yeah, I may or may not have asked previously on the idea of areas where there are lots of water affecting the foundation of these basically stations and affecting their readings. But I just, when you were explaining it, started thinking about, I suppose mudslides could also affect those in areas that also have a lot of water too.
Hmm.
Not
To
that,
to combat this, as I mentioned previously, it every 10 minutes it records. So if something major happens, if you can and there's no signs of an earthquake happening anywhere else, it can be relatively assumed that it shifted because of either water or water in the ground, groundwater, so to speak, or mudslides. It generally, obviously, any point of data that I talk about here cannot be taken alone to predict an earthquake. It's all very contextual. You cannot do any part of this without, you can't have a singular data point from any of these without data points from at least one of the other ones and say an earthquake is happening. And obviously, you have to take into account eyewitnesses. That makes it sound like it's a crime to be an earthquake, but I can't think of a better term.
you see, that
Uh,
tectonic plate went to prison for a solid 10 years, and they had to do about 200 hours of community service before it was allowed to continue its movement or its exist. You know, it works. The joke works. It's fine. Yeah, but
Actually, the trigonometry of alignment arrays. This is what Okay, let's order this properly.
What do you mean? I can see it just fine behind that.
This is what you have to do if you don't have an OS, is you have to correct it um by looking. Well, this is if you don't have an OS that's perpendicular. Well, that's drastically not perpendicular. Is you have to take the angle to the fault strike itself in order to get, well, the proper angle. And obviously you would
Hmm.
record what plant the fault strike is at previously. Now back to our analogy section.
Oh no, we're going back.
For this part, for both of the surface mounted, if you will, we're not talking about electronics, but I'm just using the term surface mounted detection systems. We can use the first 10 seconds of this video.
My favorite part of it, the part before uh
Well, actually, you really can't in terms of alignment arrays because, as you can see, there's really no permanent offset. Now we're seeing some permanent offset. So, and a surveyor who came here would be able to see not only this massive,
House is just renovating the land. It's under new management. It's okay. It's fine. He's not
not,
actually performing a military action. No, he's just renovating.
but they would not only be able to see Bowser's massive evil base, they would also be able to see that the ground itself has shifted, and they could measure just how much it had shifted through the use of alignment arrays and theodolites. See? I told you that this analogy would make sense,
It's a
which
perfect analogy.
which it definitely does make sense. Um,
I'm so glad that it didn't include uh quote normal Mario.
I am honestly amazed. Shout out to Mario for doing all of the extra effort to do such an amazing Chris Pratt impression.
He's really good at it.
He must have watched all of Parks and Rec, Guardians of the Galaxy. I'm pretty sure Chris Pratt was in both of those.
I mean, I know he was in Guardians of the Galaxy.
Um, this is off topic, but I'm gonna look this up just to make sure I'm not spreading the information.
Yeah, that
Okay, it looks like, are there two movies just called Jurassic World? Oh, Jurassic
um
World Dominion, not Jurassic, just Jurassic World. If I can say the word Jurassic. Yeah, he was in Parks and Rec.
I've
But
not
yeah,
seen it.
it's honestly it's amazing that Mario went through all of the effort to get such a good Chris Pratt impression.
You know, he is really good at it. Yeah. You know, I never knew he had it in him.
Anyways, we are on to our next topic. LiDAR.
Ooh. Ah.
LiDAR is used for studying primarily earthquakes that rupture the surface. This is this here is if I can expand the picture a bit more so it's more readable.
I'm just thinking of the enhance. Enhance.
This is the Heaven Lake earthquake that happened in 1955. As you can see, it created quite the surface disruption here. This was not here before the earthquake happened. And
Jeez.
as implied, um, LiDAR can only be used to measure earthquakes that rupture the surface. Obviously, it's a surface measurement system, much like INSAR, which we'll get to later. So obviously, you can't really You can't really just go, hey, an earthquake happened. It didn't rupture the ground, but let's see what the satellites make of it. That doesn't work like that. You cannot see a non-rupturing earthquake from space. So you just sort of you have to. These will only work with stronger ones.
It would
But
be in. Oh, sorry.
oh, you go, you go.
Or I was just saying with the not being able to see underneath like an exposed surface.
Hmm.
It, I'm not sure if this is a thing that exists, but it would be interesting to see if they had a version of basically LiDAR, except it utilizes radio frequencies, like very low wavelength, or
We
yeah,
have
very.
been able to take X-rays of the Earth. I didn't want this episode to go on for over half an hour to 40 minutes, so I didn't go into it that much.
I suppose that, yeah, that can get pretty based off of, just having a knowledge of radio frequencies and then being able to penetrate through surfaces.
Mhm.
Yeah, that could get kind of complicated compared to how LiDAR. Yeah, that compared to LiDAR is kind of complex.
Yeah.
LiDAR is kind of very nice in its simplicity.
Sorry, I just needed to adjust some stuff at my desk here. Okay.
Just has one of those
So,
little birds that like sip out of a cup.
so we can not only use this analogy for surface mounted things, but this change can obviously be seen on LiDAR as well. It is a very massive change. If we skip ahead just a little bit, Bowser here creates semi-similar effects to an earthquake. We don't have to worry about him getting a star.
Oh
But
no.
Bowser there created semi-similar effects to an earthquake, which could be seen on LiDAR. If we had the satellite data, we could probably estimate roughly the magnitude of that earthquake.
Hmm.
So welcome to the Calculus Corner and INSAR. This is
Yay.
admittedly the portion of this presentation and podcast that I have done the least research on. So this is going to be a rougher analogy and a rougher explanation. My apologies for that. But you can see here, these are two equations. Let's order this one to front for now. These two equations are used to roughly estimate the surface deformation of an earthquake. So in order to estimate that, we have to apologies. I just realized that just in case sorry if sorry listeners if you could hear my Discord going off in the background. Um
You've got mail.
I have muted Discord for now. So sorry if you heard that earlier. Anyways, back to calculus and back to INSAR. INSAR is specific enough, but it's not super accurate, much like LiDAR. I forgot to mention this. LiDAR isn't super accurate. Generally, the ground measurements are a lot more accurate than satellite measurements are, just in general. Obviously, there's a lot less possibilities for um, interruptions, for any sort of statistical blip. I accidentally triggered the mute function on my headset.
Oh no.
We're keeping it in because I don't want to spend an hour editing this.
Yay! Laziness. No.
But yeah, just quickly running through this equation, and this is probably where most of the audience is going to check out. I give you full permission to just completely check out for this. Go find something else to do. Come back in roughly 10 minutes.
And then just nod and shake your head and just say, "Yes, I understand." At the end, when it's like, "That's the end," everyone will believe you.
So h represents a Heaviside step function, which if I can pull up my notes on Heaviside step function here, it's generally considered, oh no, we are once again exposing that this is definitely the first take of this
Oh, oh,
episode.
oh no, we're being exposed. Hide the evidence.
Definitely
Bury
the
it.
first take of this episode.
I mean, nothing. There's nothing there. You don't see anything. It's empty. Blank canvas.
So, so Heaviside step function is something like this, where this is welcome to Khan Academy, by the way. This is what a graph of a Heaviside step function looks like. Uh-oh, my computer just said all changes saved. I don't know what it's referring to.
Oh no.
I can only hope that it's not something that's gonna interfere with the podcast. But at a trial by fire, we're going with it. So these are generally defined by a piecewise function. H equals. Okay, so I presume it's something with the website, the all changes saved thing, because it popped up again. Yeah, all changes saved, so
Oh, that corner there.
yeah.
Yeah.
The thing is, it's right above like the menu and the date and stuff, so that's why it scared me.
All above your taskbar.
Yeah. That's generally what it's defined as. At the value of 1, x is greater than 0. At the value of 0, x is less than or equal to 0. Basically, if it's below 0, it's 0. If it's above 0, it's 1. And if it's in between, it's about a half. So
Um,
that's your only defined value. That's at, I believe this is perfectly like a half. I admittedly did not do enough research on Heaviside step functions in specific.
wouldn't it be x is or greater than 0, then x is less than 0, not equal to, because there are two holes.
Well, according to Wikipedia, this is how it's generally defined.
Oh, yeah, I was just
Oh,
thinking
this is the
maybe.
half maximum convention understanding of the Heaviside step function. There is, um, basically, data would, if there would be an issue if this value was undefined, you just put it in the middle.
Oh, I
But if
see.
you
Okay, you just
can
come up with
deal
an
with it,
you just
if you
come up
can
with an
deal with it being
affirmation.
undefined, it's just gonna be 0. Or
Okay.
if you just need to if that value is important in some way. So, in other words, this is also fine.
I was just thinking about like a normal step function. How
Mhm.
that Okay, I see now.
This is also fine. It just depends on which convention you're using. Admittedly, I did not research into the paper I referenced for this, which convention they were using, from what it looked like, because it's time you're trying to calculate the surface deformation at minus time at 0. I presume they're just making it function like a switch. So I guess it would be the conventional it would not be the half maximum convention, it would just be your this general convention.
Hmm.
So yeah, that was the calculus corner section, I'm pretty sure. The rest I don't think you can consider super advanced calculus. The Heaviside step function is obviously a part of operational calculus, but I'm pretty sure by pre-calc we could understand the rest of this function.
Yeah.
Because as you can see here, the one that's measuring the portion that's measuring coseismic displacement and a logarithmic function. The logarithmic function represents the post-seismic deformation, and c is the coseismic displacement. Sorry, I'm taking a drink of water. That's why there's awkward silence.
You need to hydrate. You have to hydrate with a nondescript brand of water.
Even though it's just filtered tap water.
No, we could have made a case like a joke about your company could sponsor kind of a
I mean, you could. I use a branded filter. They
no,
could sponsor us.
just like a text to speech thing over you saying the like type of water you're drinking. Hey, nondescript brand is my favorite water.
I can't even think of any brands of bottled water now. I was gonna make a joke where I just say a random brand, but I can't even think of any.
I mean, I can, but I mean, that I don't. Our water company is very picky about.
I just realized I think I said A and T were represent post-seismic deformation. Oh, and to clarify, post-seismic deformation means overall deformation of the Earth, not just surface deformation, which is why it's a separate value for psi than it is for A and tau. T still represents time. V is the long-term linear deformation rate, so obviously that's why it takes into account time. And V is a constant. It's the reference offset in observations. So basically, if a satellite's most likely not going to be positioned directly in front, not in front, but above where an earthquake happens most of the time. So you do have to have that constant in there just to account for if you're off quite a bit. However, this is only for the original earthquake. This does not account for all overall earthquake, the entire earthquake, because most earthquakes that are big enough to cause surface deformation have aftershocks. So this is where our second
The
equation
bigger one.
comes into play. As you can see, the v of t plus b and the Heaviside step function and the equation that vaguely looks like compounding interest is all generally the same. The only difference is it's T of 1 instead of T of 0 because this is for the aftershocks, not the original shock. No, this is all the same, but because it's accounting for more than one shock, T of 1 represents the original shock, T of 0 represents the earthquake not happening. C of 1 is the coseismic displacement after um the coseismic deformation of the original earthquake. So as you can see here, this is all generally the same. This is all generally the same. I hope that I hope that my screen recording is recording my mouse movements. Otherwise, it's not going to make any sense whatsoever.
This, you're not pointing anything. Oh, that
But
would be
yeah,
funny though.
but the main difference you can see is this Riemann sum just sort of slapped in the middle here, and that's to total the entire displacement from all the other earthquakes. So as you can see, this is the same Heaviside step function as before, but I'm just taking into account the coseismic deformation, but it's I instead of 1. And I indexes, of course, with each earthquake that follows. It starts indexing at 1, as discussed earlier.
Not the square root of -1. That'd be very
Yes,
different.
to clarify, I as in this as meaning index, as in the first letter of index, not imaginary numbers. To
Getting
clarify.
funky with their earthquakes.
So, as you can see here, this can be used to graph coseismic deformation of the surface using INSAR. And here is a graph of generally what that looks like. You can also rework it, obviously, to get each variable if you know what the surface deformation is, which I believe is actually um, the main point of it, because you can see the surface deformation via INSAR. And a lot of the other variables you can't really see using INSAR because INSAR is, well, it stands for Interferometric Synthetic Aperture Radar. So, if you know what aperture means, it's steepness. So, it measures steepness, so you really only see the surface deformation with it, and you get the other data points most of the time from things like creep meters, alignment arrays, or LiDAR in some cases. So, most of the time, these equations are actually reworked backwards. And this is how you can get data like this, where you can get magnitude, relative location, the center depth, the strike, the dip, and I believe it says rake, using these equations. And to round out this podcast, which is encroaching on 40 minutes now,
Oh, yes.
you can measure the deformation that comes from demolishing the city, and then figure out every single variable in this equation using the power of INSAR. So this has been arguably the worst episode of this podcast so far.
I mean, a lot of the time I was because I think we've already kind of, just subtly hinted at there being multiple takes so far. I just most of the time I stayed quiet to make sure we didn't get off track. for explanations and stuff, and I want to stay quiet for you explaining things. But yeah,
Yeah, so I'll be 100% honest. Well, this was a decently fun episode to make, especially after I realized the amazing analogies I could make.
I was really wondering how many times you can compare it to the trailer of the new Super Mario Bros. Movie, or the new trailer of the Super Mario Bros. Movie. I don't think they're making a movie based off of the DS series, which was first a Wii series, but
Well,
that's a different episode.
to my knowledge of the Super Mario Bros. Movie, it's not based off of any particular game per se.
No, that's why, like, clarified.
Well, it's based off of the Mario universe as a whole, which includes the new Super Mario Bros. So
Yeah,
arguably, it's a new Super Mario Bros. Movie
I mean,
by process of association.
technically, yeah. I don't think we got off topic enough.
So yeah, welcome to not welcome. Thank you for
You've been here for
watching.
a while.
Thank you for watching this 40-minute long It's Dangerous to Go and listen to this obligatory hard science episode, Earthquake Edition.
It definitely. I'm sure they definitely feel like they just got here. I'm sure that's the case.
Um, I hope you learned something. I hope that my Bowser Earthquake comparisons made sort of sense.
I'm sure it really solidified their understanding of the concept.
hmm
Because I mean, what shouts
I
out?
mean,
I understand a topic by being
I mean,
able to reference Bowser while doing so
I always understand a concept better if I'm given examples of how it's applied.
in Mario specifically.
Well, not specifically Mario, but just overall.
Oh yeah,
Mario,
you're narrowing down your
Mario,
field.
oh, platformers in general are always nice for analogies.
I mean, Celeste really teaches you how gravity works.
Yep, definitely doesn't give you unrealistic expectations of gravity at all.
What are you saying? I can't double jump?
Join us next time when we discuss the physics of double jumping.
Where I go into an existential crisis.
Anyways, that's all. We haven't figured out an outro yet.
So we should just make a
Goodbye.
random sound and just be like, bye.
That would only work if we actually had a soundboard. We're not that professional yet.
Yes, we need to configure OBS and be like, whoa, it's so professional. I pressed one button. We need like an auto tune button and then just start talking the entire time just in auto tune.
Yeah, thank you for sticking around through all of this. Welcome to the unceremonious outro. Goodbye. How do I stop Craig? Forgot how to stop Craig.
Oh no, let's see.
Oh, maybe the big red button that says stop recording.
Yeah, that might do it.
I'm leaving this in. Goodbye.
Okay. See ya.